Hello everybody, welcome back to another video. Today we're going to be talking about reinforcement learning. I'm really excited to talk about this topic, so let's not waste any time and get right into it. This video is going to be split up into two different sections: the theory that will be in this PowerPoint that I'll explain briefly, and then the code, which is the hard implementation with a visual demo that's super cool. So if you're familiar with the theory or just want to stick around for the demo, you can skip to the demo. All the timestamps are down below. Feel free to skip around. All right. So in machine learning, we have three real sects. We have supervised learning, unsupervised learning, and reinforcement learning. Supervised learning is learning the function mapping from some data x to some target value y. Unsupervised learning is being presented with x and y having no labels, and learning to identify patterns within the data. So this is looking at some data and identifying patterns. This might be clustering or looking at the different correlations between the data. While supervised learning is like regression, trying to find a line of best fit. Reinforcement learning, that data is a little bit different. Let's talk about how the data is represented in reinforcement learning. So in reinforcement learning, you have an agent that interacts with some environment. Now, the environment sends some state to the agent, and I'll explain all of this terminology again in a moment. The agent takes some action onto the environment based on the state it was given by the environment. And then, based on the action the agent performed in some state, it receives a reward. So really, let's refactor this diagram, and these are the main definitions. The agent is the decision maker. The environment is the world where the agent learns and performs actions. The action the agent performs is some process the agent can perform within the environment, and we'll provide an example. A reward is, for every action, there is a corresponding reward. And just a state is a current situation of the agent within the environment. So again, the agent interacts with the environment sends some state to the agent takes some action based on that state and receives a corresponding reward. Now let's think of an example that illustrates this, like in real life. So a really simple example would be a person with a stick throwing to a dog. Now the dog is the agent, and the environment is the person with the stick in some grassy field. Okay? So the states in this case are sitting, running after the bone, and stick retrieved. The actions in this environment are do nothing, run, and retrieve stick. Now notice how the states describe the environment and the actions describe the agent. The agent is doing nothing, the agent is running, the agent is retrieving the stick. While in the state, nothing's happening, basically sitting, running after bone, stick retrieved. That's describing the entire environment, not just the dog. Now the rewards is the dog receives a bone after the stick is retrieved. So let's review this one last time. States describe the entire environment, what's going on. So the dog is sitting, nothing is happening. The dog is running after the bone, the stick has been thrown, and the stick has been retrieved, and the dog is going back to the owner. Now another example is Atari games. So the objective of an Atari game is to achieve the highest possible score. The possible actions are up, down, left, and right, assuming we're playing some of the more simple Atari games. The state is the pixel inputs of the game, so actually what graphically is on the screen, and the reward is just plus minus in the score. So as the score goes up, it's a higher reward. As the score goes down, it's a lower reward. So these are two fundamental examples of reinforcement learning that can be implemented in real life. Now, the question rises, how do we mathematically formulate a reinforcement learning problem now that we know what a reinforcement learning problem looks like in real life? So, all reinforcement learning problems are Markov decision processes. Let's look at this Markov decision process. So we have two states, don't understand and understand, and two possible actions, study and don't study. Let's say, before a test, you don't understand a topic and you decide to study. Well, the probability that you don't understand is 0.2, as you see above the study action. The probability that you do understand that topic is 0.8. All right? And the reward if you do understand the topic is 1, and the reward if you don't understand the topic is -1. Now, if you don't understand and you don't do anything, you don't study, the likelihood that you won't understand is 1. Because if you don't study and you don't know something, there's no way of you knowing it. It's not just going to pop in your head. So this is like a simple Markov decision process, and every reinforcement learning is a manifestation of this structure. So now the question arises, okay, we had these rewards, -1, 1, 0, but we might not want to have rewards 0, 1, 2, 3, 4. We might want to calculate them in a certain way. So the total reward number is the sum of all immediate rewards we get for taking actions within our environment. So that's just an R total number, the sum of all immediate rewards we get. But there are two issues with this formulation. The first one is rewards can go to infinity, and we're trying to maximize the amount of immediate rewards we can receive. And number two, immediate rewards and future rewards are weighted the same. But you want to kind of be greedy towards immediate rewards because you're chasing over something that will give you a reward instantly rather than something that will give you a reward in the future. So the way we solve this problem is we have some variable gamma that looks like the squiggly y you can see on the left here. And gamma is called a discount factor. It essentially makes future rewards worth slightly less than immediate rewards. So previously, we had our formulation where R total equals RT plus 1, and T is just a time step. So we're just adding all of our immediate rewards. And our new R total, the one on the right, uses the gamma discount factor. Now, I made a mistake here. It should be squared. So for every next time step, the power of gamma increases by 1 to decrease the value of future rewards. So now we actually need an equation that tells us what action to take in a given state. We know how to calculate rewards. We have a basic understanding of the theory, but now given a state by the environment to the agent, how will the agent know what action to take? And this is where policy and the Q function comes into play. So a policy is a function that decides what action to take in what state, and we want to find a policy that maximizes reward. Now, a Q function, or the Q function, defines the value of taking action A in state S under some policy pi. And the most basic way of formulating this is, let's say we had a table where on the left we had some states, and on the top we had some actions, and they had a corresponding Q value. And this Q value tells us the value of that action within the given state. How valuable is it? Like, will it yield a higher reward? Will it bring us closer to the terminal state, to the state at which we want to end at? All right? And we create this table, and we'll be able to use this table to say, okay, I'm in state 1. What action that maximizes the Q value or the reward in this state? So now we come to the Epsilon-Greedy Q learning algorithm. And this is the algorithm we're going to be implementing today. Now, what does epsilon mean? All right, so epsilon basically defines the balance between exploration and exploitation. So we're going to have to find the given rewards and Q values for every action state pair. Remember, we have these pairs, action state pairs. We're going to have to find that Q value, and the only way to find that Q value is to explore in the environment, do a bunch of different actions and see what happens. That's called exploration. Exploitation is looking at the table and finding the highest Q value and determining, okay, I'm going to do the action that yields the highest Q value. And now you're probably asking, why don't we exploit every time? Why don't we just use the highest Q value in the state table, in the action state pair that will yield us the highest reward every time? Well, our Q table is empty when we initialize the environment. We need to explore the environment, fill out the Q table, and then at a certain point start exploiting our Q table. But until we haven't explored, we can't exploit anything because that Q table is empty. So Epsilon-Greedy essentially has some variable epsilon that is a number that tells us how much we should explore versus how much we should exploit. And once we start filling the Q table, that number goes lower and lower and lower and tells us to exploit more and more and more. Now, the point of this tutorial is to give you a very, very light introduction to reinforcement learning. There's a lot more math behind the Epsilon-Greedy Q learning algorithm and a lot more about the Bellman equation. There's just a lot of math involved, but I really want to give you a light introduction, so I've omitted a lot of that. Now that we've reviewed the principles and kind of the theory of reinforcement learning, I feel fully equipped to teach you guys how to implement it in code. And so the problem we're going to be attacking today is the CartPole problem. It's a very classic and famous problem in reinforcement learning. Basically, what we have to do is teach a cart to be able to balance some pole. So the pole has to stand upright and the cart has to move at some velocity or some speed to keep the pole within some range theta. And it's a pretty complex problem, but once we actually implement it in code and see how our algorithm is improving and improving and improving over time, it's going to be really, really cool to see the results. So let's get right into the code. Believe it or not, for today's demo, we only need 4 libraries. So we're going to need NumPy, obviously. I think you predicted that. All right, NumPy is NP. We're going to need gym, time, and math. Let me make this bigger. All right, so the way you can install these libraries, if you just press the blue plus button, you press that and then go to terminal. All you have to do is, you're going to mainly want to install gym. You might have math and time pre-installed. You just do pip install gym. And I already installed it, so it'll say requirement already satisfied. But for you, it'll say gym and then some loading bar. So if you have any issues installing gym, just let me know. And also install NumPy. So same process, pip install NumPy. And math and time should be pre-installed, but if they're not, you can install those. Is everyone good on installing all of those libraries? Good, great. Okay, so now let's take a look at what our environment looks like. This is where the cool stuff starts. So we'll define our environment as env, and we'll use the function gem.make, and the name of our environment is CartPole v1. All right, so the first thing we want to do is understand what our action space is, validate it. Our action space is just the amount of actions we can take. So action space.n just denotes, okay, we have n amount of actions. So if we print that out, let me just import this first. If we print that out, that will be 2. So remember, we discussed 2 possible actions, left or right. So everyone good on that? Yeah, what's up? What's the gym library for? Gym library is going to be for our visualization. So that's the library that imports all the environment related stuff. So you'll see that there's going to be like a live visualization here, and that's what the gym environment does. And believe it or not, the people who developed these reinforcement learning libraries are from OpenAI. I don't know if you guys are familiar with OpenAI. It's a really famous company that deals with AI solutions. They made GPT-3 codecs, a bunch of really, really cool stuff. All right, so now let's kind of experiment with like what our environment might look like. So I'm gonna go to this file here. Let me scroll up. I'm gonna take this code here. This is just example code. You don't have to copy it. I just want to show you what the environment looks like. So these are commands that you're gonna have to make yourself familiar with. Observation. Observation is going to tell us the action that we're currently performing in the environment, the state, the reward, whether we're done or not, and also some other important information about how our environment is reacting to some action. Okay, so this is just an example of how we can test the environment. So to render the environment, it's just env.render as we defined it previously, environment. And then action, this is just taking some random action. Action space.sample, taking some random action. I encourage you to copy this code because you're going to be able to, I want you to be able to visualize this on your own computer. And then our reward and whether our program is done or not, basically updates based on what action we take. We print our observation to reward whether we're done or not in some info about the environment. And if we're done, we print our program has finished after X time steps. Okay. So this yields a pretty cool visualization and will get you familiar with what our environment looks like. So take some time to copy this down and then we'll get to the algorithm itself. Looks like we have something in the chat. Can you be closer to the laptop? It's difficult to hear your voice when you're away. Yes. Unable to find blue. The blue plus sign should be on the top left part of the page. Ah, sorry about that. Anyone have a Windows computer who's running this right now? You see the blue plus sign, right?
I think so, yeah.
It's at the top left.
Yeah.
I think someone's having an issue with that. Let me see. But this person's having trouble accessing the terminal.
Oh, check if they have that tab pulled up on the outside.
Make sure you have, Ravi, make sure you have that tab pulled up on the left side. You might have to drag it out. So has anyone run this code yet? If you run the code, you get this really cool visualization. This is what our problem looks like. Yeah, make sure to pip install pyglet. I forgot to. So it should just be like this: pip install pyglet. It's a dependency for Gym. Okay. So no, you don't have to import it. So if you run this, restart the kernel. If you run this, you're going to get a super cool visualization. And these numbers here, let's talk about what these represent. These are states. So the first state is the position of the cart. The second state is the velocity of the cart. The third state is the angle of the pole. And the fourth state is the angular velocity of the pole. All right. And there are certain ranges in which these fall. So like from here to here. What's up, Ben?
The visualization is like super cool.
Yeah, I can kind of see it. Though,
Okay. Can I see what yours looks like?
And also for the button thingy, it's this menu on the side. You might not have moved it.
If you want to read it, but double click it, it's next to it. And this will restart the kernel.
Okay, now it's working.
Yeah. Oh, I still speak. Oh, action space dot sample. Right here.
You know, so that blue button thing, it probably just, you have this, but,
Okay, cool.
yeah.
You got it?
Uh,
So restart the kernel again because you don't see the visualization. Just
kernel.
yeah. You can also just press the double escape button.
Then meant to just stop at the end of it or what?
Yeah, it's meant to just stop like that.
Okay.
Yeah, there we go.
Alright, good.
So
It just like starts swinging.
yeah, it just starts swinging because you're not actually doing anything in the environment. You're just initializing it at some random point and letting the pole just swing and swing around. You're not actually doing anything. Anyone having trouble visualizing that? Getting that ready? You guys good? You got it? Good? Good? Okay.
The CartPole user is like a specific some name or we have randomly assigned it.
The name CartPole?
Yeah.
That's just the name of the environment. Like, are you referring to gym.make CartPole?
Yeah.
All right, so yeah, so OpenAI Gym has different environments. So it has like a mountain car environment, a CartPole environment. There's just a bunch of different environments. We just specifically chose this one. It's a simple environment to deal with reinforcement learning, and the visualization is pretty easy. But there are environments with more states, more actions that I encourage you after we finish this, go explore those and try to retrofit the Q-learning algorithm we're about to build to different problems. You'll see that there's some pieces of code that we have to write that are specific to this, specific to the amount of actions and states that we have in this. So remember, 4 states, 2 actions. Let me review the states one more time. Cart position, cart velocity, pole angle, and pole angular velocity. 1, 2, 3, 4. This is the reward. This is whether the game is done or not. All right. Now let's get into the implementation of the algorithm. Beforehand, again, does anyone have any questions? I just want to make sure. Okay. Let's get into it. All right. So there are going to be a lot of variables that we're defining initially here that we're going to be using a little later. I'll give you a brief introduction into what each variable means, and then you'll see how we implement them a little bit later. All right, so first we have a learning rate. Define that as LR. And just set that to 0.1. That's just a standardized value. In machine learning rates are usually set to 1, 0.1, 0.01. We just chose 0.1. It's an arbitrary choice. You can adjust learning rate based on what you see in the results. It's just a choice right now. So we'll define the learning rate as basically the size of step we take in adjusting our actions. All right, so the learning rate is the size of step we take in adjusting our actions, and that corresponds to how we adjust our Q table. So the next variable we need to define is our discount factor. Does anyone remember the name of that variable? The little squiggly y? That's right, gamma. And we'll define that as 0.95. All right. And this discount factor just tells us like the importance of immediate rewards versus future rewards. And the specific algorithm we're implementing is called an Epsilon-Greedy policy because it's greedy towards immediate rewards versus future rewards. All right, so now there's some other basic variables that we need to define. Oops. So epochs is traditionally how many iterations something runs. We'll say 60,000 iterations. Total time we'll define as 0 because we're going to be needing total time to measure basically how long it takes for the CartPole to solve the problem or how long a certain action takes. We also need a variable called total reward, so we can calculate the reward for each time step. We'll set that to 0 as well. And then we need a variable called previous reward, so we can compare our firstly calculated reward and our previously reward and see the discrepancy. So yeah, if you want to follow along with him, just because you came late. So yeah, if you need any help, I can come help you while everyone's coding a little bit later. All right, so those are some basic variables we need. Or again, epochs, the amount of iterations we have, so 60,000 total time, total reward, previous reward, are pretty self-explanatory. All right, now we're going to get into something that's a little bit more complicated. We'll define a variable called observation. And right now it's just a list with 4 inputs. Can someone give me a guess of like what this might correspond to? Yeah, the different states, right? So pole velocity, pole angle, stuff like that. And then we need another array, array called step size. All right, and I'll explain what the function of this is. It's a little abstract to explain. Oops. It's a little abstract to explain, but I'll try my best to explain it. So observation and step size define that list and that array. And then we need to finally define our epsilon value. Epsilon equals 1. And our epsilon ek val. We'll set that to 0.9995. All right. What is epsilon? Let's remind us. It's associated with how random an action is. All right, and then exploration is basically decaying, and we will get to a point where we're only exploiting. Right. So epsilon basically tells us how random an action is. Explore, so it defines like whether we're exploring, whether we're doing random actions, or whether we're exploiting, whether we're doing actions that are most valuable to us. And this decay value will tell us how quickly epsilon decays, how quickly epsilon decreases. And there's a whole another formula for that. So the next part of the code is not as intuitive, but before we do that, let's just run this little block of code. It's really important that you run each block of code because you might write a bunch of code, and if you don't run it, it's going to give you errors and you're like, I didn't do anything wrong. So make sure you have all of this written down. Do you guys have any questions about the variables we initialized? Yeah. Yeah, sure. What do you need to see? This? What do you need to see this? All right, I'll go back to the previous part before. Do you want to take a picture? By the way, once you're done with this, this is uploaded on GitHub, so you guys can check it out on GitHub if you want. Yeah, do you want to take a picture of that? Okay, let me go back to the definitions part of the code. So is everyone done with this part? Does anyone need any help with this? Like explaining or what's up?
Epsilon decay.
Yeah, do you want me to explain why we chose this specific value? Well, there's a equation that we're going to get into that uses these 2 variables to calculate a new epsilon value. This is really, I'll explain it a little bit later, but it's just, I don't know if you're going to. Okay, so now let's initialize our Q table. So we'll create a variable called Q table. Okay. And we're going to use a function called np.random.uniform. Let me explain what this does. np.random.uniform, there's going to be arguments here. It basically gives us values from a uniform distribution. All right, random values from a uniform distribution between 0 and 1. We need to use this just to randomly initialize values in our Q table. We're not interested in initializing like all zeros or all ones in our Q table. We just want completely random values, all right? All right, so did you guys get that part or do you want me to say it again? Yeah, so np.random.uniform is a method from NumPy that allows us to grab random numbers from a normal distribution between 0 and 1. And so there are a couple of arguments here. So because it's between 0 and 1, our low variable will be defined as 0, our high variable will be defined as 1. And then the size of our Q table will be observation plus env dot action space dot n. All right, it's not too intuitive, but the basic idea is, let me just get the parentheses right. The basic idea is we want to get random values in this Q table, and we want to initialize this Q table to the length of the observations, which is the different states, and the width of the action space. All right. So length of the observation, length of the observation, width of the action space. All right. Hopefully you guys got that. And if we, hold on, if we print this, we'll see that we'll get a bunch of literally random numbers. All right. Random numbers between 0 and 1 in this array format. And the arrays are too large, but they're of size 4 by 2. Okay. So we've initialized our Q table. Is everyone caught up to this point? Great. Now we're getting to the exciting stuff. Get hyped. Let's get it. All right. Now, the last boring thing we have to do is discretize our state. So right now, the format that OpenAI Gym gives us our state is not something that we can manipulate. It's going to give us a box format. So the box format is just a different format that OpenAI Gym provides for displaying state spaces. We need to change that box format to a discrete format, and that discrete format we'll use to input into our Q learning algorithm. So we have to make some method called discrete state. All right, and our inputs are just some state, and then this is just a one-liner. Discrete state. You can define the variable however you want. Equals state divided by step size plus some array. And then we just want to return. I spelled return wrong. How is that? All right. Why are we doing this? We're trying to change the type of our state to a discrete state. And essentially, oh, I just misspelled as type. Essentially, we want to return a tuple with 4 values in the format that OpenAI Gym likes to process. All right, and that's how we do that. I don't want to get too in depth with this because we have a little bit more complex stuff to get to. But basically what we're doing is we're taking the format of the state that we get from the environment and converting it into something that OpenAI Gym likes to deal with rather than this. Because if you don't convert the state to discrete, then you'll get an error in the code. Okay. Let me see. I saw a question from Zoom. Oops. Let's see what we got here. Yeah, so step size will be used a little bit later. Step size will be used in relation to learning rate and how basically how much we adjust our Q values. You'll see that in a minute. Okay, so now we are getting to our algorithm. All right, so I'm gonna comment everything for you guys so you understand what each part means. Let me sit down here. All right. So first, we're going to do some iterations. So we're going to say for epoch in range epochs plus 1. Remember that epochs, we had 60,000 epochs, and here we're just iterating through epochs. All right. First thing we want to do is take the time. All right. So we have we'll define some variable time initial. We'll say t initial equals time.time. Make sure you have that library imported. It's really important to use time.time because that way we're going to measure the length of each action, right? The time length of each action. All right, then we're going to have to use discrete state, the method that we just used. So I'll say discrete state. This is how we get our state, all right? So let me just say this here. So we're getting the discrete state for the restarted environment, so we know what's going on. So we're restarting the environment, we're saying, okay, the environment is completely clean. What's going on? What's the discrete state of this environment, okay? Now we need some variable, some Boolean, done. We'll set that to false. If you guys have ever worked with games, you'll know you'll always need some Boolean so that if some action triggers the quit functionality, you'll just exit that while loop and the game will end. All right. So this is just some control Boolean. All right, we'll be taking advantage of this a little bit later. And then we have a variable called epoch reward. So for every epoch, for every iteration, we have some reward that we're going to be adding to. All right. And so for every 1,000 epochs, we are going to be printing out some string. All right, so if epoch modulo 1,000, so equals 0, we'll print episode. So basically, we're going off the number that each episode is 1,000 epochs. An episode is just us saying epochs are the amount of iterations we're doing, but episodes are 1,000 multiples of epochs. So episode plus string epoch, all right? Any questions till now? I'm just on some basic coding here. If you guys don't understand some of the control structures here, I'd love to explain them. If you have any questions. Good? Okay, so now we're getting into the real stuff. Oh, chat question. Can you explain the last epoch? Oh, the print statement. Yeah. So we're just basically taking the amount of epochs we have and dividing them into bite-sized pieces because we're not going to measure the reward or the time for every action in every epoch. We're only measuring the reward and time for every action for a set of epochs, for every 1,000 epochs, for example. All right, because printing that out over and over again would be too tedious. All right, so now we're going to start the game loop. So we'll say while not done. So while done equals false, that's also a possibility. If np, oh, let's indent that. If np dot random, some random number is greater than epsilon. Here comes our Epsilon-Greedy stuff. If some random number is greater than epsilon, then we'll take the argmax of our Q table with our state. Okay, discrete state. What are we trying to find here? We're trying to find the maximum reward for some given state. So we're going through all of the actions and saying what action has the maximum reward. Are you able to see that? Should I move it for you? Let me move this, right? Scroll it up. There we go. Better? Okay. So we're trying to find for some given state, what is the maximum reward for a given action? And we assign that to an action, right? And then if that random number is not greater than epsilon, then we'll say action equals some random action. Now we know our action space is 2, but maybe it's variable and we want this code to be reusable, so we'll say action space dot n. We really know that action space dot n is 2, but we can just say random 0 to 2, okay? So here we're just deciding if some random number is greater than epsilon, we'll define our action as regular action. That's the maximum action for some given state. This is exploitation, this is exploration. Let me denote that for you guys so you kind of understand that. This is exploitation, finding the largest reward, and this exploration. All right, some random action. Okay. Now what we want to do is we want to update the environment, right? Do you have a question? Yeah.
Q table for discrete, what does that?
Okay, so Q table of discrete is going to give us just this argument, right? This argument is going to give us a list of actions. Then we want to look through the list and choose the maximum reward, and the maximum reward will correspond to the best action, right? Good, yeah. Okay. And then this is just some random action, and we're using NumPy, basically NumPy methods. These are really useful for array manipulations, list manipulations, anything. NumPy is super useful. Now we're going to update the environment. Oh, we have a question here. Why are we doing numpy.random.random epsilon? The reason why we're doing this is we're just saying is some random number greater than epsilon, and if it's greater than epsilon, take the argmax. It's just some arbitrary way. It's just some way to determine whether we're doing a random action or a discretely like motivated action based on the reward, the largest reward, using epsilon. So we're taking advantage of epsilon to randomize some number compared to epsilon, and if it is greater, then we take the max, and if it's not, we just do some random action. Now we update the environment. So we'll say new state reward done equals environment.step our action. I want you to recall, I'm sorry, I just moved in the middle, but I want you to recall to back here how environment.step some action returns 4 variables: observation, reward, done, and info. Okay. We're not really concerned about info, so that's why we said this. All right, we're not actually going to call on it, so the variable name doesn't matter. So that's why we had those 4 inputs to one method call. So environment.step action. Environment.step means take X action. All right, so there are 2 actions. Let's take this action and assign it to our new state or reward, and whether we're done or not. All right, and this is going to be able to update the new state, calculate some reward, tell us that the game is still going on. All right. Here's where it gets interesting. So we are going to say epoch reward. We're going to now update the reward. Epoch reward plus equals reward. We're going to define our new discrete state. And we'll just use our method discrete state, new state. Okay. Now our state has been updated. Let me scroll up for you guys. Just tell me to scroll up, yeah? Now our state has been updated. Our reward has been updated. Now what we want to do is render the environment. So we'll use the same if statement as before, but instead of printing out episode as whatever, we want to render the environment. Okay, so we'll do environment.render. Okay, and this just initializes the visualization for this epoch, all right? Is this all understood? Do you have any questions about this, guys? Let me check the chat. Any questions? Yeah, what's up?
Can you just go over the function of discrete state one more time?
Sure. So the real point of discrete state is to take the box type. The box type is the type of the state that we get as our input, and do some calculation to convert it to the discrete type. All right, so a discrete type and box type, these are types that are coded into OpenAI Gem's library. We need to do some manipulation to our state to make it basically usable within our code. Because if we don't do that manipulation, we can't access the values within the state list. So this way, this allows us to be able to access the number values within the list of states. Yeah. I know it's a little confusing, but if you go to OpenAI Gem's documentation, there's a lot more information about box types, discrete types, and stuff like that. All right, so now we render an environment. Great question, by the way. We render an environment. The only thing that we need to do now is just to update our Q table, right? So we're gonna say if not done again, if the game is still running, we'll have some max new Q. All right, and we'll say np.max Q table, our new discrete state. All right. The purpose of this is to get a new max action, all right? And then we need our current Q, which is just our Q table with our discrete state. That's our action space. All right, and I'll explain all of this in a minute. I just want to get all this code done so we can explain it fully. And then our new Q value, 1 minus our learning rate, multiplied by our current Q, plus our learning rate, multiplied by our reward, plus gamma, times max new. All right, and then what we'll do is we'll finally update our Q table, and we'll say Q table discrete state plus action equals new Q. Okay, this is a little confusing, but I want to go back to the pseudocode. Let me make sure that everyone is done writing this. Let me go back to the pseudocode that we reviewed previously. So if we go to our PowerPoint presentation and we go to the pseudocode, really what we're focusing on is this little part. We're selecting an action, take the action, observe the reward and the next state, and we're updating our Q table for some state in action using this formula. All right. This variable is the learning rate. This is a reward. This is gamma. We're taking the max of Q and some new state A and subtracting it from our current state, from our current Q value with state S and action A. All right. So this is the way we update our Q value in our Q table using this specific equation. So if you look at the code you wrote, it's not going to be exactly the same, but it's going to be pretty similar to what this looks like. All right, and the final thing that we didn't do is we need to set our state to our new state. All right, so the way we do that is, oops, I shared the wrong thing. Let me share this. The way we update our state is we say discrete state equals new discrete state. Now we define new discrete state right here. So we're just updating our state. All right. So what we just did was we calculated a bunch of variables. So we could actually input that into the equation that allows us to update our Q value. All right, and you can see here that we're only updating one Q value. So we did all of these calculations, we updated our Q value, we updated our state. The only thing left to do is deal with epsilon, okay? So how does epsilon play into this whole equation? So really what we just did here, we looked back at the pseudocode, we saw it's kind of corresponding in some way, the calculations might be a little different. But really, let's break this down one more time. 1 minus the learning rate multiplied by the current Q value plus the learning rate times the reward plus gamma times the max new Q. Now remember, we introduced gamma because we wanted to discount our future rewards, all right? And that's what we're doing here. We're multiplying gamma by our future reward and adding it to our current reward, which really corresponds to our original equation, which was RT plus 1 plus gamma times RT plus 2 plus gamma squared times RT plus 3, and so on and so on and so on. So now, how does epsilon play in the equation? Let's get to that. So we'll start with an if statement. If epsilon is greater than 0.05, and then if our epoch reward is greater than our previous reward, so pre-reward, that's how we defined it, right? And our epoch is greater than 10,000. All right, then we'll recalculate epsilon. Using our epsilon decay value. So math.pow allows you to do exponents. And then we'll just do epoch minus 10,000. All right. Yeah, you can. You can technically, but math.pow allows you to just input variables a little bit easier. And I just wanted to show you guys how to use math here. But yeah, two asterisks is also good. Yeah, sure. You can do that if you prefer. And then we'll print our epsilon value every 500 epochs. There's more math associated with epsilon, choosing different values, how we recalculate epsilon, manipulating, these epoch numbers in that number in that initial if statement. But really the point here is to show you that epsilon is some variable that we use to determine whether we're acting randomly or if we're acting with some purpose. And as the model gets better, we continually update and decrease epsilon till we get to a number where epsilon is so low that we're only really taking the argmax of our Q table. And at this point, we're done with the algorithm. So good stuff, we're done. Now all we need to do is just print out a couple of more things like our time initial, our time final, calculate some of the episode rewards, and then you'll be able to see your long-awaited, fully rendered animation of how your model continually updates over time. I'm telling you, this is one of the most rewarding things about machine learning, seeing the results. It's going to be really cool. So the last thing we need to do, yeah, sure, scroll up, down, sure. All right, so we'll calculate the time final by just saying time final equals time.time, as we did previously with time initial. We'll say the episode total time is just final minus initial. All right. And total time plus equals episode total. All right, now we'll calculate the total reward. and we'll just do plus equals epoch reward. And our previous reward is just our current reward. Now, again, we iterated, here, I'll wait for you guys to write that, but we iterated for we're doing stuff every 1,000 epochs. So we'll say if epoch modulo 1,000 is equal to 0, then we'll calculate the mean time for actions within that 1,000 epoch range. So we'll say mean equals total time divided by 1,000. Pretty self-explanatory, and then we'll just print average time. It should be plus. All right, and then what we want to do is set total time equal to 0 because we're calculating total time for every 1,000 epochs. And then we'll do the same thing for mean reward, right? So mean reward equals total reward, equals total reward divided by 1,000 again for every 1,000 epochs. And then we'll literally just copy this, do the same thing. Average reward. And then we'll just say mean. Set the total reward to 0. And then we exit the loop completely and just write environment.close. All right. Should be good. Let me run. I don't know if that will change anything for us, but. No, yeah, you're right. That's it. That changes everything for us. Yeah, demo works. All right. So now if you run your demo, you'll be able to see the cart balancing the pole. It takes a bit of a while to render each time. So there's delay between the amount of epochs it runs. But check this out. How cool is that, guys? Are you guys able to run the simulation? It's slow. You can actually play with the numbers, so it renders every epoch. So if we want to play with the numbers, and let's say have it render every epoch. So go to the code and eliminate the piece of the code that says if epoch modulo 2000 equals 0, and we just say environment.render, and then it's just going to give us this really jittery thing. Oops, what was that? Oh, this slash here. It's going to give us this really jittery. Yeah, that's what it looks like. You can see how phenomenal this is, the progression of the cart balancing on the pole. You'll see that the time for every iteration gets longer and longer over time. Sometimes it's shorter and shorter, but you'll see after 60,000 iterations, the model will be like fully trained and we'll be able to balance the cart on the pole. It will take a while for it to get to where we want it to be. That's why we only rendered every 2,000 iterations. But you're basically witnessing live a model learning with reinforcement learning. And I really think that's really cool, like how we went from the conceptual explanation and visualize it within code. There were a lot of errors on the way. I appreciate you guys helping me with that, but I think this is pretty cool. Now what we'll do is we will exit this and put back that clause. All right, and we'll increase it to 5,000. All right, and then we'll see the model being trained. If you want to see cool machine learning videos that make demos just like this, make sure to check out these videos.